Good evening, everyone. Welcome to our Tucson Amateur Astronomy Association first Friday of the month meeting. This is a general meeting and we have members attending this meeting and we also have guests attending. Our guests are on Facebook and we just wish to welcome all of our Facebook people to enjoy the meeting with us. And also when you have questions, just enter those into your system in Facebook and we will be able to read them here and we will address them to our speaker here. For our members, we ask that you stay muted through the presentations, and when you have comments or questions for the speaker, then please enter those into the chat and we will address those to the speaker, and we will make sure that we get everyone's questions addressed. So it may take a little time at some point because we may have multiple questions at one point, but we will make sure we get to your question. And we're delighted to have all of you here tonight. I'm May Smith. I'm president of the association, and Terry Lappin is with us tonight. And Terry is doing double duty tonight. We usually have a separate person doing Facebook and a separate person doing Zoom, but Terry is doing both of those responsibilities tonight. So we're going to kind of proceed a little bit slower, probably with switchovers between things, but I don't imagine there will be any other difference. I'm getting some kind of message. I don't know. Am I not loud enough? Okay, apparently the sound is okay. So anyway, we will proceed to our speaker tonight. And we're just delighted to have Dr. C.K. Chan with us tonight. And Dr. Chan is impressive in all kinds of ways. And one of those is not only the work he does, but also how you describe it. Dr. Chan is a computational astrophysicist, which I think sounds extremely impressive to most of us. But he's a delightful person to talk to and a really enjoyable speaker. So Dr. Chan, would you begin your presentation? Are you ready to screen share?
Yeah, I'm ready to do so. Can people see my screen?
Yes.
And let me bring this up to presentation.
We can see your backgrounds. Yes, now this is much better. Thank you.
Okay, great. So good evening, everyone. It's my pleasure to share with you today some of the work that I've been doing in the last couple of years. So as May introduced me, I'm CK. I was actually an undergrad student at the U of A. So I lived in Tucson for a very long time. And it's great that I can share you many of the astronomy things that we develop here in Tucson. So means that I'm a computational astrophysicist. So what that means is I use computer to simulate astrophysics system. So so before I dive into these very impressive pictures we have in this title slide, let me just tell you a little bit background of black hole on both the theoretical side and the computation side. So nowadays, I will say most people actually accept black holes exist, and most people will even agree that we believe almost in the center of almost all galaxies there live a black hole. But this is not always true. And in fact, black hole was a theoretical prediction from Einstein's general theory of relativity. So I have a simple animation here representing if you have a flat space-time, if there's no mass around, then the photons will just travel in straight line in this space-time. But when there is a heavy matter it could be a sun, it could be a planet that curves the space-time, then particles and photons will move in curved space in around the central object. So there is a very well-known sentence by John Wheeler, saying that the space-time tells matter how to move and matter tells space-time how to curve. So this is the basic idea of general relativity, and this is our leading theory of gravity. Now, using this theory, Swalchi actually solved a solution, a very strange solution, that there is a surface called the event horizon, that when photons pass that surface, they cannot come out. So it's also John Wheeler who quoted the word the black hole, because this kind of very strange astrophysics object, this kind of very strange space-time, they will just attract everything, not even light can escape them. Now, however, as you saw in my title slides, nowadays we can see black holes. So why is that? So let me go to my computational side and just explain to you what happened around a black hole. So what I show you here, this is a computer simulation. There are actually two simulations here. The box in the front ground, this transparent thing, this is a plasma simulation around a black hole. So at the middle, there is a black hole, and around that, we let fluid, gas, flow around the black hole. And it turns out this gas will got heat up to very, very high temperature, up to 10 to the 10 Kelvin, so that they become ionized, they become plasma. And this plasma will interact with magnetic field, create a lot of very interesting phenomena, including generating a funnel like this, and then having the emitting plasma around that. Now, just having this so-called accretion flow around the black hole is not enough to turn that into an image. So in theoretical calculation, in computational calculation, what we do is we draw a grid of pixels. So this is, think about this as your digital camera, that you have a camera that many pixels on them. And for each pixel, we use computer to follow the photons backward to the black holes. And then when we go through this very hot plasma, we take into account how they emit. And then at the end, after we do this calculation, we will have a simulated image of a black hole. Okay, so although black hole, they will attract everything, including light. But what happens is around the black hole, there are very hot plasma. And this hot plasma emit light from radio wave to optical light to even X-ray and gamma ray. So it is this hot plasma around the black hole allow us to see the black hole. Okay. All right. So this is actually my own work. So this is a simulation. So what you are seeing here, this image corresponds to this grid of pixels here. But when we're doing a computer simulation, it doesn't have to be a static image. We can simulate movie. So let me just run this movie for you. Can people see this running? Yeah, so what we are seeing here, the blue stuff, these are actually X-ray emission around the black hole. And this pink, purple thing along the pole, this is the region with very strong magnetic field. And then this purple region is the accretion flow. So even before the Event Horizon Telescope observed black hole, theorists or computational scientists like me actually you already have a sense of how black hole should look like based on theory. And also, we don't have to just simulate the black hole at a single wavelength. We can simulate them across a lot of different wavelengths. So in this movie, the left panel here, this is radio wave. The black hole accretion flow is actually not transparent. So this looks like a cloud blocking the black hole itself. But in a higher frequency, shorter wavelength, so the black and white image here, this is actually the the frequency that the Event Horizon Telescope is observing. And at this frequency, we are able to see the central black hole. And in some other frequency, we can also see black hole. So this movie shows you that actually black hole is emitting light in all kinds of frequency, and they are very variable. And there are a lot of interest in understanding on why the black hole is varying, what this corresponds to in the physical environment around black holes. Okay. So I mentioned to you the Event Horizon Telescope a few times already. So having the theoretical prediction is very exciting, but this is not the same as actually capturing the black hole. Because black holes, they are very small on the sky. So even with large telescope that we have in Arizona, we are not able to resolve this black hole. So what happened was, theorists got very excited about the simulation, and then we convinced enough people, enough observers all around the world to join force to take a picture of the black holes. And actually, this is me here, and then you can see there are many, many more people. This is more than 200 people in our collaboration, more than 60 institutes all around the world. And within Tucson, this is our local team at the University of Arizona. Again, myself is in this team, but we also have a lot of even undergrad students joining our research. So this is very exciting that, of course, the science is exciting, but the fact that we are bringing in students to work on this project, the educational aspect is also very exciting. So, what do we do in this collaboration? I mentioned earlier that the black hole is very, very small on the sky. So in order to take a picture, we cannot just use a normal camera, normal telescope. Instead, we use a technique called very long baseline interferometry. So the idea is the black hole will emit light at different frequency, and the wavelength we pick is 1.3 millimeters. So, and when those radio waves reach the Earth, we gather those information on different radio telescopes all around the world, and then we record the waveform from the black hole on actually hard disk. And then we ship these hard disks all together to our data center to processing them and to reconstruct the black hole image. I'm going to show you a few more slides on the details of how this works. I mentioned to you that we are using 1.3 millimeter wavelength. So why do we want that? So this pretty animation here actually tells you why. So right now we are looking at a simulation of the black hole at the center of the Milky Way. And we are looking at some very long wavelength radio wave. But at this wavelength, you cannot see the black hole. The accretion flow, the plasma around the black hole is not transparent. So you just see a cloud blocking the black hole. So if we take a picture at this wavelength, we wouldn't be able to see the black hole. But now as the movie goes, I'm moving to a higher frequency, shorter wavelength. And as we go to this higher frequency, the accretion flow starts to become transparent and it disappears. And at this end of the movie, I'm actually at sorry about the slide skipping. But at the end of this movie, I'm at 1.3 millimeters. So that is the exact frequency that the EHT is observing. And at this wavelength, the accretion flow is transparent. And we can see through all the cloud and see the central black hole, the central shadow here. Okay, so this is the reason the Event Horizon Telescope picked that specific frequency to do our observation. Now, I mentioned a few times the black hole is very small, but how small that is? That is as small as putting a donut on the surface of the moon. So this is very tiny. Another way to describe this is if you put a point of sand, you put it on Phoenix, and you try to find the sand from Tucson. This is how small that the image of black hole is. And this is another reason why we can't use normal telescope, even as big as the one we have in Arizona to see this black hole. All right, so I think I will skip this because this is, I probably don't have enough time, but I want to bring up that the Event Horizon Telescope actually observed many, many black holes on the sky. Our main targets, there are two main targets. One is called Sagittarius A star, that is the supermassive black hole at the center of our Milky Way. Another black hole is at the center of the M87 galaxy. And then other than these two black holes, we also have many other black holes that we are observing. Now, unfortunately, these other black holes, they are very far away, so there's no way we can resolve their event horizon. We cannot see the surface that the light cannot return to us. So when we look at this black hole, very often we only see the base of the jet, we see a block, but we cannot see a donut. But for Sagittarius A star and for M87, these are two big black holes very close to us. So they are big enough, well, they are big enough on sky. They are still very small, donuts on the moon, but the Event Horizon Telescope is powerful enough to resolve them, and then we can see the central darkness of these black holes. All right. So physically, the Event Horizon Telescope is your many radio telescopes around the world. So I'm showing you a couple of them. So you may recognize this SMT, the submillimeter telescope at Arizona, and also the U of A operate the South Pole telescope. We actually have faculty member go to the South Pole, spend time there to build the instrument. And then we also rely on your telescope in Hawaii, in Mexico, in Chile, and also in Europe. And for the EHT, we keep expanding our array in order to have better resolution of black hole. So in 2018, we add a few telescopes. We add a second telescope, the Keep telescope, also in Tucson, also in Arizona, only you're an hour driving from Tucson. And then we also have the South Pole telescope and a different telescope in Europe. So this is now our current array. And actually, the EHT just took our 2022 observation just last week. And we have multiple astronomers who are from different parts of the world who travel to Tucson and with us this week. So this is pretty exciting. Because we actually send students to the South Pole, so I want to also just showcase a couple of pictures to you. So this is Jun Hong. He used to be a student here. He's now at Caltech, and you can see he dressed as a penguin and when he traveled to the South Pole. And this is another picture of Dan Ronnie. He's a professor here at the U of A. Jun Hong and Mel, so another student at the U of A. So we actually send people to this very remote location to set up the instrument in order to take picture of the black hole. All right, and this is a very beautiful picture of the submillimeter telescope that I mentioned earlier. All right, and this is the new Keep telescope that you just recently joined the array. And I'm going to showcase a couple of pictures from 2017. So this is significant because 2017 was the first time there's enough telescope in the Event Horizon Telescope collaboration that we can take a meaningful picture. It actually took us more than a decade to build this array. At the very beginning, we only got 3 telescopes. So there's no way for those early observations to take an image of the black hole. But we did gather data to tell us that we expect a black hole and expect a central a donut shape. But 2017 was our big year that we can really do the observation. Okay, and then so I mentioned earlier that the telescope array is global, so we have many telescopes around the world. And then when we do the observation, we record the radio waveform to actually hard disk. And then there are a lot of data. Just the hard disk that store the data weighs your half ton. And the data volume was so big that we cannot transfer them through the internet. So we just put them in your shipping container and use FedEx to send them back to our data centers. So we have 2 data centers. One is at Haystack Observatory near MIT, and then the other one is in Germany. And at this telescope, we combine the raw data we get from the telescope, do a step called correlation to remove the noise. And then we need to calibrate the data to remove the systematic error. And then we start doing the image reconstruction. And it's only after this many steps that we get the final black hole image that everyone knows about. Okay. So there's a lot of work, a lot of programming. So even though you as a computational astrophysicist, at the beginning I did simulation, but my computation skill turns out to be important when we need to put together the software to processing the data. So I guess I actually have two different hats that on one hand, I run computer program to simulate whatever theory we have. But on the other hand, I also write program to processing real data. All right, so I think I will skip these slides because I think I'm running out of time. So I will go through very quickly. Just a second. Yeah, I will go through this. And then I want to mention, I keep mentioning this computation infrastructure and the telescope, but the people in the collaboration is also very important. And in fact, when we do the image reconstruction, because we are very careful and then we don't want to fool ourselves, we worry about our image algorithm will create a black hole image that is not true. So what we end up doing is we split the scientists into 4 different teams. We didn't talk to each other for months. And for each team, we developed our own image reconstruction algorithm. And only after a few months of work, after we test our algorithm independently, then we came together into a conference and we compare the result. And very luckily, all the different teams, we actually construct very similar black hole image. So this is really happy picture we took at Harvard when people compare our result and our result are consistent with each other. So that was the first time that we are sure that we successfully took a picture of black hole. Okay, so I will also skip these slides, but I just want to tell you, because the image, the data we gather from this telescope, they actually log pictures that we take from cell phone. There are some data that we call visibility. And in order to turn the visibility data into image, we rely on computer algorithms. So there are infinitely amount of solution to this black hole image. And our team is very careful in comparing all of these different reconstruction results to make sure that what we see is scientific accurate. Okay, so these are different image reconstruction from different software pipeline and from different days of the observation. And you can see, although there's difference in the details, but then the core feature, there is a ring with a central darkness. This feature is robust across all days, across all algorithms. So we are very comfortable that we actually have a picture of the black hole. Okay, and this is our scientific result. We are very happy that many people around the world saw this result, and we even have cartoons who incorporate this result. So and put the scale on top of it. So if you put the solar system in this black hole, then the sun is only this tiny point at the middle. And this circle here, this small circle, is the orbit of the Pluto. So, wow, this is a very big black hole. The black hole itself is bigger than the whole solar system. But we need to remember this black hole is also very massive. This is actually 6 billion solar mass condensed in such a small area. So big black hole in physical size, but because this is very far away from us, so it's very tiny on the sky, and you require a telescope as big as the Earth in order to resolve it. All right. So having just the image is not science. It's very good that we have the image, but we also want to do some measurement from the image. So the scientists in the Event Horizon Telescope also do model comparison in order to compare simulations. What you see here, this is many numerical simulations of black holes. So this, the idea is very similar to the first few slides I showed you. We use supercomputer to simulate the plasma around black hole, and then we put in different assumptions of this plasma, and then we create this grid of image. And then we compare this many image with the image we observe. And then by this comparison, we can conclude that what are the physical parameter of the black hole. So some of the conclusion we got is the black hole is spinning. We know the direction, the orientation of the accretion flow, and we also know the black hole spin is pointing toward us. So all of this measurement require comparing supercomputer simulation with image reconstruction from this very massive telescope array. So I guess things go full circle. Okay, so what I show you is what we have done so far. But of course, the Event Horizon Telescope is keep improving. So these are a couple future steps we are taking. We are working on the polarization information of the black hole. It turns out those information can tell us about the magnetic field structure around black hole. So they're scientifically very interesting. And then the other thing is I show you the image of the M87 galaxy black hole. I haven't shown you the black hole at the center of the Milky Way. So I guess we are working on that, and we will share that result to all of you very soon. And then we are also trying to observe at higher frequency because the accretion flow will be even more transparent on those frequencies. So hopefully we can learn more about black hole with those new observations. So yeah, so this is all I want to tell you. And I guess I will take the question from all of you. Thank you very much.
Okay, I don't have any questions in the chat right now. So those of you who have questions, would you please enter them in the chat? And Facebook people, would you please also type in Facebook your questions? And we will be glad to address them. Okay, we have a question from David on Facebook. And he says, is a black hole a star?
It is a very good question. So there are many types of black holes. So when a star runs out of its fuel, it can collapse into a black hole. So in those sense, when a black hole is a few times the mass of the sun, it is is a die star pretty much. But then the interesting thing is for this very supermassive black hole that I just showed you, actually nobody knows where they come from. They can be formed by your smaller black hole just merging, or they could be there all the time from the beginning of the universe. So in that sense, they are not really stars, or at least we don't know where they come from. So.
Okay.
Mm-hmm.
Do we have other questions? Okay, yes, we have one from Howard. And he says, is the dark center of the interferometric image a good representation of the actual diameter? Whoops, my computer just moved and so it changed where I am. Okay, a good representation of the actual diameter of the event horizon.
Okay, that is another very good question. So this is not exactly the event horizon, but this is a projected version of the event horizon. So the way you can think about this is because the black hole, you curve the space-time. So when light travel near the black hole, it actually got banded and got lengthened. So the image around the black hole got distorted. So the event horizon is actually smaller. The event horizon, if the unit of the event horizon is 2, then the diameter is in unit of 5. So what you see here in the shadow is actually slightly bigger than the actual horizon, but they are proportional to each other. So.
Okay. Question from Doug. So you have observed and imaged the 2 black holes. Can't image the others too far away. Will there be improvements to the equipment which would allow imaging of more black holes?
Mm-hmm. There is another thing very interesting because we are working on that. So the event horizon just keep improving because we will install your detector on more telescope, and we are also building new telescope to increase the sensitivity. Now, unfortunately, if we stay on ground, if we stay on Earth, we cannot make the Earth bigger. So we cannot increase the resolution further. So if we stay on ground, we can only resolve the M87 black hole and Sagittarius star. These are the only two black holes we can resolve. Now, however, if we can go beyond the diameter of the Earth, then we can image something that is smaller. So the next step, one of the farther away step we want to take is to go to space. If we can put radio telescope in the space, then the distance between the space telescope and the Earth telescope can be longer than the diameter of the Earth. And in those situations, we will have higher resolution and we'll have your possibility to resolve farther black holes.
Okay. Heidi has a question. Your image resembles a mirror image of a tornado. Are there any that have more than two sides, top and bottom?
Yeah, it's very interesting. My son, I showed the visualization to my son. He also said it looked like a tornado. So what happened there is there is angular momentum on the plasma around the black hole. So when the plasma fall onto a black hole, they need to conserve that angular momentum. So it's like people dancing. If you bring your arm close to you, then you will spin faster. So this is the same idea. So when the plasma fall very close to the black hole, they spin very fast and move at the speed of light. But when the plasma is orbiting, the pole along the perpendicular to the rotation, those can create a funnel and create a region with very strong magnetic field. So those tornado that you refer to actually a magnetic field along those poles. So now, because of the symmetry, because of this rotation, we won't really have another stripe of tornado come out now. But in some other situation, then when the angular momentum is weak, then you may not have a accretion fold. You can have just plasma falling on top of the black hole. And in those cases, it is possible to have magnetic field escaping all kinds of direction. So if we try to visualize those, then yeah, it's possible to have many tornadoes coming out.
Okay, thank you. Vernon asked, will the EHT be taking data this year?
Yes, so I actually mentioned that near the end of my talk. So we actually did almost 2 weeks of observation in the last 2 weeks. So yes, we were taking data. And I think that at the beginning, the weather was not too good, but in the last few days, it was pretty good. So we are pretty excited of this new round of data. And in my last night, I also show you we are improving our equipment, and we are observing in even higher frequency, shorter wavelength. And this is actually the first year we are observing in those higher frequencies. So again, this is very exciting.
Okay. A second question from David on Facebook. Is there more than one black hole at the center of the Milky Way?
Mm-hmm. Very good. So I would say before the work of the EHT and the more recent Nobel Prize work that we monitor the orbits of star around the central black hole, there was multiple theory. Some of them suggest that we could have two black holes, but I guess with the latest observation, I think most people think that we have only a single black hole at the center of the Milky Way. And also because of the EHT observation, we are also pretty sure there's only one black hole at the center of M87. But then for the further away black hole that the EHT is also observing, some of them can be a binary supermassive black hole.
Okay. David Ledviv from the club asked, how about a radio telescope on the moon?
That is very exciting. So if we do have a radio telescope on the moon, then we will have a very long baseline. The baseline is so long that we can resolve very fine structure around the black hole. So in that case, we wouldn't just see the donut, we will actually see very fine details. But on the other hand, when we have this very long baseline, we also need to have the baseline in many different angles. So it will depend on which black hole we are observing. in some direction, we will be only able to resolve straight, but not reconstruct the full image. So it really depends on what black hole we are looking at. But it will be great to have a radio telescope on the moon.
Super. Okay, from Crystal on Facebook, is there another life or time or space inside the black hole?
That is a wonderful question. Nobody knows. I mentioned at the beginning that black holes are theoretical predictions, and actually in some of the black hole solutions, you can extend the space-time to another region, and you can even have something called closed time loop. So you can go into the future, but then you end up at behind in the past. So there are a lot of strange things can happen under the framework of general relativity. But right now, these are only theoretical predictions. I will say most physicists will think there's some contradiction in the theory that we need to resolve. So most people don't believe those solutions are real. But on the other hand, they are allowed by the general relativity. So I guess you rely on better astrophysical observation, better understanding of the universe in order to tell if those are true or not.
Okay. Dan asked, is the James Webb Telescope going to be used to view black holes?
Absolutely. So at least for the proposal, for the project that I know, there are at least 2 observations of Sagittarius A star. One is led by the Event Horizon Telescope that we want to observe the black hole at the center of the Milky Way at the same time using James Webb and the Event Horizon Telescope. So that will be super exciting. And there's another project actually led by myself. So I propose to observe the Sagittarius A star at the UV, at the ultraviolet light. So that is a very tricky observation because there are a lot of dust around the center of the Milky Way. And that is the reason there's actually no observation today to tell us how bright is Sagittarius at that wavelength. So my proposal is to do that observation with James Webb and then do some modeling of how the dust will scatter the night. And hopefully we can get an upper limit on the emission at the frequency. And once we have that, it will help us to understand the environment around the black hole.
Okay, Garrett on Facebook asked, is it possible there are emissions from the center at extraordinarily high frequencies that we have not been able to see yet?
Yeah, so when you say center, I'm not sure if you refer to the black hole image, the central dark region, or are you talking about the center of the Milky Way? But I can answer both. So for the central darkness region, so that darkness is actually universal across all wavelengths. So I can even just bring up my simulation here. So let me share my screen again. So in this simulation, the right-hand side is X-ray. So this is very high energy radiation, but you can still see the central darkness around the black hole. So this is true because of the space-time structure. The central darkness is, at least for this kind of black hole, they're the projection of the event horizon. So the emission in that region is actually dimmer. So that's the reason we see the dark region. Now, in terms of the central region of Milky Way, there are actually a lot of stars around them. So when we observe them across all different wavelengths, we can actually see those stars. So in that sense, yes, we do have a lot of emission, very high energy emission.
Okay. Thomas asked, why is so much data collected? Is it because of the high frequency? Are you scanning a large area of the sky around the black hole?
Mm-hmm. That is a very good question. It's kind of technical, but it's very good. So I would say there are 3 major reasons that we need so many data. One is just the nature of the technology we need to resolve the black hole. Again, the black hole is very small. So we cannot just use a CCD, use a digital camera to take the picture. In order to gather the data and construct the image, we need to take advantage of the fact that light is actually a wave. And we need to actually take in, we are recording the radio waveform from the black hole. So just doing that will require very high frequency sampling and gather a lot of data. So that is one reason, it's just the nature of the observation. And the other reason is the black hole is very dim, and then the instrument, the universe is noisy. So most of the data we gather, they are actually just noise. And we have to gather a lot of data in order to airphase out the noise to get the actual signal. So that is the second reason. And then the last reason is, I talk about this baseline. When we have multiple telescopes, we can join them, we form a baseline, form a data point. But we only have around 10 telescopes all around the world. So that doesn't give us that many data points. So in order to reconstruct the full image, we need to wait until the Earth rotates so that the telescope pair will give us different data points. So because of that, in order to take a black hole picture, we need to observe a whole night until the Earth rotate enough. So that is the third reason we are capturing so much data.
Okay. Heidi asked, what happens when two black holes come together, or does that even happen?
That happens. So for the stellar mass black hole, so for those black holes formed by when the massive star die, they become stellar mass black hole. And we actually observe this stellar mass black hole come together, orbit around each other and merge. So when they merge, they release a lot of energy. Some of those energy go into gravitational waves. So sometimes you hear news about LIGO, detecting gravitational wave, detecting black hole merger, detecting neutron star merger. So those detections come from two black holes, two neutron stars coming together. Now, theoretically, we can have two supermassive black hole merge. It could happen when two galaxies come together, and then the central black hole just come together and merge. But I don't think we have direct observation of those. But we do have numerical simulation, using those to simulate the evolution of galaxies.
Okay. Ben says, would the use of the cloud negate the need to ship hard drives via FedEx?
Yeah, so unfortunately, because the data volume is just so big, so it turns out FedEx is still the highest bandwidth way to move data around.
Okay. Brad says OJ 287 is too far to allow the black holes to be resolved, but can EHT resolve the binary? If so, it would be an awesome test or illustration of general relativity to watch them orbiting each other.
That is an excellent point. And in fact, the EHT does observe OJ 287. Even though this is not one of the target we can resolve, but because it's a bright enough source, and as Brent said, it's potentially a binary black hole. So we are very interested in observing this. And in fact, right now within the EHT, we have a team specifically working on this source, and we expect the paper to come out in this year or so. So so stay tuned.
Okay. Well, thank you so much, CK. You have been just really patient with our questions. And I think maybe you're coming back later to meet with our members. Is that right?
Yeah, that is my plan, but I do think I need to drive home. So if you don't mind, then maybe I will sign off, drive home, and then I will call you again. Is that okay?
That sounds wonderful. I think Terry's all set up for that, to reconnect with you, for that. So we just appreciate your being willing to come back for some individual time in a breakout session with our members later. So thank you so much.
Yeah, no problem. I'm very happy to share my work, and I see a lot of very great questions. So I'm very happy that people are curious about black hole. So
Great, thank you.
My pleasure.
One more question. There is one more
Mhm.
question.
Oh, is there? Did I miss one?
Is it possible, this comes from David on Facebook, is
Okay.
it possible that dark matter comes from black holes?
That is another great question, because I would say maybe 20 or 30 years ago, there actually your scientific paper discussed that possibility. And I think for maybe a decade or so, people didn't think that is possible. I don't remember the argument. You know, I'm not expert in that field, but for some time people rule out that possibility. But I do see a couple new papers coming out again to discuss this possibility. So I will say, you know, it's possible, but people are still working on this. So we don't know the answer for sure.
Great.
Thanks.
Thank you so much. We will see you later then, CK.
Okay, great. Yeah, so bye everyone for now, and I will call back later.
Okay, thank you.
Bye.
Okay, we have our second presenter tonight is Dr. Mary Turner, who is TAAA's Chief Observer, and she's going to share her quarterly seasonal report of what's up in the sky. So Mary, are you ready for screen sharing?
I think so. We'll find out momentarily.
Okay, super.
Okay, so let's do that way, and that's the wrong screen, so let me minimize that, and okay, okay, so where's the one? There we go. Is that sharing okay?
I'm not seeing it.
Okay, so I've got clicked on screen 2 and I clicked on share.
Oh, something else is happening. Yes,
Okay.
there we go.
We got it.
Okay. So,
Okay, so if you're ready, that's great.
okay, and you wanted me to be done by 1950, right, Terry?
Yes, that's the schedule, I think.
So
Okay.
yeah, 7:50. Yep.
Okay, so, well, good evening, everyone. Glad to be with you again, even though it's still virtual. Sorry for the mess up last quarter, but I got home to give the presentation, and house under construction up the street had knocked our cable out. But I'm here for this quarter. So what we're going to do is talk about some things that we can look at over the next month. And obviously same type of information we typically look at, a little bit of constellation information, and then some different objects to take a look at. And obviously this time of year, we have outstanding views of many galaxies and clusters of galaxies and all sorts of interesting things. So that's probably what we're going to concentrate on mostly. But I'll start with a little bit on the constellation Virgo. And Virgo is, again, one of those constellations that, I mean, you can sort of accept that that might be representing a somewhat human figure, sort of figure, 2 legs, 2 arms, something like that. So it's not as weird as some constellation pictures, but it's a bit of a stretch. And again, my headset's not working right. Some other views of it as well, including looking at some of the stars. So, you know, if we want to call that the head, I got to admit, and if we look at this sort of picture here, I'd say rather than the Virgin, it looks a little bit more like Little Red Riding Hood, but hey, I digress. So let's talk a little bit about Virgo itself. Not much blood and gore associated with Virgo. Virgo, the Virgin, has been associated with many different goddesses and legends throughout history, throughout the different mythologies we tend to take a look at, but always tends to have the same sort of goddess of fertility aspect to it. if we look at it in the stars, it's also located somewhat near Libra, the scales of justice, and so we can connect it to the goddess of justice, with where we have justice on one hand and punishment in the form of Spica on the other. But again, going back significantly far into history, Sumeria and Babylon, same area, of course, have Virgo as the goddess of fertility much earlier than 2000 BC. Where this comes from is typically, as with the constellation stories and lore in ancient mythology, it represents a seasonal effect. And when we talk about the goddess of fertility, we're talking about that time between the death of life, in particular agriculture, that occurs in the winter, and the springtime renewal of vegetation, and that's in that time frame when Virgo was the dominant constellation in the sky. But it does cover or is also seen in many other cultures as well. To the Hindus, Virgo is Kauni, who is the mother of the god Krishna. But going back to the mythology we typically think about, which is Romans, which stole it from the Greeks, which stole it from the Babylonians, who took it from their ancestors, the Sumerians. In Babylonian mythology, it wasn't referred to as Virgo, but as Ishtar. And Ishtar was a goddess, the goddess of fertility, but her husband was killed by winter. Of course, winter in itself doesn't kill you. Winter had the form of a wild boar, which was necessary to kill her husband, Tammuz. And then Ishtar follows after him, or chases after him, through the 7 gates of hell to try to rescue him and bring him back. And each time she proceeds through one of these deeper and deeper gates headed in towards Hades, the situation on Earth becomes more desolate, darker, colder, more and more lifeless. Problem is, of course, she does make it all the way through the 7 gates, but no one, either God or human, has ever been able to return, or had ever been able to return from Hades. So although Ishtar was able to go through the 7 gates, survived barely, was reconnected with her husband, but she couldn't come back. She was imprisoned there. And the problem was, as she was imprisoned there over some period of time, what happens when the goddess of fertility is trapped inside of Hades? Well, those things the goddess of fertility is responsible for, like spring and plants and even children, sort of fall by the wayside. So as long as the goddess of fertility isn't on Earth, you're not going to have plants growing and sprouting in the spring. You're not going to have children born. And obviously, it wasn't going to take very long after this process started that life could potentially perish completely on a very cold, dark, and desolate Earth. That's obviously not something the gods were looking forward to. So they got a little bit concerned, and then they made overtures towards the Queen of Hell, Ereshkigal, to sort of persuade her, shall we say, to release Ishtar. And she did agree to do this, realizing that all the gods of heaven joining together against her, she probably wasn't going to come out on the winning side. So she decided to give in. And then Ishtar said, fine, but I'm not going without Tammuz. So he was also revitalized and given life again. And as they then proceed back, they still have to now reascend through each of those gates of the 7 gates of hell. At each step along the way, the skies started to clear, the sun started to shine, the grains began to sprout, and again, springtime had returned to Earth. The interesting thing is we often see a lot of mythology that's very much in common between the Greeks, the Romans, and the Babylonians. But if we think about the Isis and Osiris story in Egypt, it's actually very similar to the Ishtar story from Babylonia. Isis was the goddess of fertility. And as we all know, that after her husband was killed by his brother, she went searching up and down the Nile to find all or almost all of the pieces of his body and to bring them back together where he would again be re-given life. She was also known as the goddess of fertility, which was why typically when you see representations of Isis, she typically is shown with a sheaf of wheat, because that's the symbol of, agriculture and the rebirth of agriculture that occurs every spring. Roman mythology, it's slightly changed, the names of the characters have changed, but Virgo is the daughter of Ceres and is the goddess of grains or cereal, but again relates back to the grains that were an important part of early civilizations. She was captured by Pluto, kidnapped, if you will, taken to the underworld. Ceres was very upset at this, so she neglected to take care of the things on the earth. Harvests were ruined, people were starving. So Zeus decreed that Virgo had to be released for part of each year during the time of planting through the time of the harvest. And then she goes into the underworld every fall. And again, the world goes dark, nothing grows, it gets cold. And again, Ceres mourns her loss. So again, it's sort of a story of rebirth in the spring, as with agriculture, going through the full planting cycle, and then of course the death, and to be followed shortly thereafter by a rebirth of the agriculture. So again, nothing overly bloody or gory. Constellation wise, Virgo is the second largest constellation in terms of area across the sky, but it also has a very low star density. Cancer is obviously the lowest star densities, not too much to see in Cancer. Sort of interesting connotation. It is also one of the few constellations that are sort of named after women. Couple of stars are notable, Spica being the primary one, but 70 Virginis was the first known exoplanetary system. Chi Virginis has the most massive exoplanet that was found, one of the super Jupiter type planets, and it does have a significant number of confirmed exoplanets, and of course the number of those continually goes up. Probably the biggest reason most of us as amateur astronomers tend to look at the region of Virgo is the absolute abundance of galaxies, because we're sort of looking out into a clear spot. There are 11 Messier objects in the region of Virgo. We also see the center of a supercluster of galaxies about 65 million light years away. If we look at that super cluster image that was a Hubble mosaic, which I've shown sometimes in the past, there are thousands of galaxies across a 12 by 10 degree patch in the sky. So, a region smaller than the size of the moon, we're going to see many, many galaxies. And obviously more than that we can't necessarily see with our telescopes. But definitely a lot that are worth looking at. And here's just a look at some of the Messier objects that are available to look at within the region associated with Virgo. And we're going to talk about a couple of the Messier objects and a couple of other items as well. Okay, so I'm going to start by looking at Messier 84 or NGC 4374. And again, here are the RA and DEC coordinates that I took out of the sky, and a couple of images of it as well. So we can see the lots of the fact that we can see a lot of the galaxies, many galaxies in this region if we look at some of what's in the background. And we can also look at some of the other, looking at it in some of the other wavelengths, which obviously we're not going to do with our personal telescopes. But again, there's a lot of information there, and there's a lot of interesting things happening in some of these galaxies. It has, there are images that will show a lot of the gas jets with a lot of energy coming from the nucleus of this particular galaxy. Probably a supermassive black hole of about 300 million solar masses within about a 23 light year region at the center of the galaxy. It's about 60 million light years away. It's somewhat dim, about a 9.1. You can see it, however, with your telescope. But if you were actually a bit closer, its absolute magnitude is closer to a minus 22.4, which means it's basically about 76 billion times the luminosity of our sun. Again, it's a galaxy. It has lots and lots of stars in it. The apparent dimension is about 5 arc minutes, which corresponds to approximately a bit more than 100,000 light years across. Okay, and I'm missing a picture. Okay, all right, well, so this is Messier 20, or the Trifid Nebula. And of course, we're not going to see a picture quite as nice, a view quite as nice as this through our telescopes, but it is interesting to look at. We can see the different types of nebulosity, the dark lanes, and this is looking at it in my old stomping grounds, the infrared. So we can see that it is indeed quite energetic, but there are significant regions of dust that are blocking our actual view of what's happening everywhere else. The reason we call it the Trifid is because of those dark dust lanes. It sort of breaks it into 3 sections. The red nebula is emission. The reflection nebula, the blue nebula, is not actually connected. The dark nebula is also somewhat different, and it's characterized separately or cataloged separately as Barnard 85. It appears to be red simply because there's a lot of hydrogen gas there. There's a lot of energy, so that gas is being ionized by this heating mechanism, and therefore we're seeing that appearance of light. It is, at the time of the light that's being imaged, effectively a stellar nursery. There are many, many very young stars. Spitzer images have shown more than 100 very, very new stars, and about 30 that are not quite as young, but we're talking very, very young stars. Earliest, very shortly, of course, shortly being on an astronomical scale of their actual condensing to the point of being able to start nuclear fusion. It's about a little over 5,000 light years distance. Brightness is about 6.3. You go to a lot of different sources or several different sources. They'll give several different numbers in terms of distance and brightness. I sort of picked an average type value. In your telescope, it is going to be seen basically as a cloudy patch. But if you let your eye acclimate to it a little bit, you'll be able to see that there's actually a big faint fuzzy there. And it's, for us, the diameter is about 28 arc minutes. So just a little bit less than that 30 arc minutes I like to talk about. Okay, okay. All right, so Messier 35. Located over here, and this is the constellation Gemini. Again, the sky's version of the Gemini image. So we're sort of over at the foot over here of the foot of Castor here. And here's a picture from the APOD. This is our open cluster here, Messier 35. This is a separate object down here. Okay. Messier object actually was seen by Messier, although Deschamps also had seen it about 20 years earlier. There are about 2,500 stars in a region that's about 30 light years across. And again, 28 arc minutes. That's minutes, not seconds, right? No. Oh. We can only see about 10% of those stars, or just under 10% of those stars in our, like a 10-inch scope. But obviously there are bigger scopes out there and we can get some really nice images. It's about 2,800 light years away. Again, it's an open cluster, not too far from where we are, which is why we get to see it as a collection of individual stars. On a relatively young scale, only about 100 million years old is going to be the average age of the stars. They are bluer in color, most of them, and that typically is younger stars that are burning brighter. And you can see here the stars are much, much yellower. They're also much further apart, but that has nothing to do with the temperature they appear to be. But bright white to blue stars tend to be younger. They also don't tend to live quite as long as the yellower, cooler stars. We're much better off that way. The fact that our Earth is a nice yellow planet says, our sun is a nice yellow star says our planet has the likelihood of getting a reasonable amount of heat for a very, very long time, as opposed to the live fast, die young type stars. NGC 2158, just for reference, is closer to 10 to 20,000 light years away, significantly further away than is this little open cluster. Okay, so let's take a look now at Messier 67, which is in Cancer. And as I mentioned earlier, Cancer doesn't tend to have a whole lot of really bright stars in it, but that's okay. Not sure there were too many objects I've ever really talked about in Cancer, other than possibly M67. This is another open cluster. Open clusters are pretty to take a look at. And here is a picture from the 2MASS, the 2-meter all-sky survey, showing the open cluster and, again, the individual stars, which is what we like to see in open clusters. The difference between M67, the open cluster, versus M35 is M35 was quite young, whereas M67 is actually one of the oldest star clusters known. Star clusters in general don't last very long. They can start out together, typically from a common gas patch, but even other astronomical objects that are much bigger, even if they're a very far distance away, will tend to break up star clusters, open clusters, in a relatively short period of time. So for a relatively small number of stars to stay gravitationally bound for billions of years is pretty unusual. So if for no other reason, that's a nice reason for looking at M67. It's about 2,900 light years away, and it's about 1,500 light years outside our galactic plane, which is why we can see it relatively well. It has about a 12 light year diameter, and within that region are about 500, again, gravitationally bound stars. And it's in Cancer, but it's on the Hydra side of Cancer if you're trying to find it in your scope. I, of course, would use the RA and DEC coordinates or simply zoom in on it that way. So now another one of the real showpieces in the sky is the Whirlpool galaxy. It is one of the couple of classic spiral type galaxies we get to see throughout the year. Whirlpool is, again, way up there. We get a really nice view of it in terms of its orientation towards us. And in this is again from the sky, but we can see there are lots of other galaxies as well, but we're going to talk specifically about this nice little spiral, or this nice big spiral. I've said that it's a beautiful object to look at. This particular picture does come from the APOD site. It does have, as with most older galaxies, it does have a companion, which is, of course, another way of saying it has a meal that it's currently eating. How that affects it over time, we will probably not live long enough to see, but obviously the structure and shape of this galaxy will be impacted as more and more of the material from the companion galaxy becomes intertwined. This object was also cataloged by Messier. Messier didn't catalog all of the items in the Messier catalog, but this was one he first he put together. But again, was also had been noted this time by Lord Ross about 20 years earlier. It is a spiral galaxy, so it's very similar to the Milky Way, very similar to the Andromeda galaxy. And by very similar, it's not just the shape, the general spiral shape, but the sizes of these galaxies, those three galaxies, the mass, the luminosities are all very similar. It's having, again, it is being affected by this companion galaxy, and you can clearly see that the companion galaxy is effectively being shredded by the gravitational pull of the whirlpool. And it is going to change what the shape of the whirlpool is. Come back in a couple of billion years, it probably won't look quite as whirlpooly. It will probably be, quite as spirally. It will probably be much more ellipsoidal, but hopefully it will last for a while longer. And Andromeda also has a similar companion galaxy that it's sort of feeding off of. We have close by galaxies, but chances are we've already sucked all of the matter out of them that we're going to for now. This galaxy is about 30 million light years away. It's about 60,000 light years across, so it is smaller than the Milky Way, but definitely something you can see with a telescope, but also you can see with your binoculars. So again, like I said, it's just one of the real beautiful objects we can take a look at. Okay, so let's go to our next Messier object, which is, again, another spiral galaxy that we'd see in the direction of Virgo. And this time it's Messier 61, also at NGC 4303. And this is an atom block picture. And this is a very, again, nice view of a spiral galaxy. We can clearly see the spiral arms, but they're not quite as distinct as we saw in the sombrero or some of the other images we see of spiral galaxies. But it's certainly a beautiful object to look at as well. And we can clearly see the concentration at the core here as well. And we can also see blue and red, which is an indication that there is still activity happening within this galaxy. So lots of active star formation occurring within those spiral arms. It is beautiful. Like I said, it doesn't have quite that structure, but just all of the activity is just amazing to look at. Again, you'll use different filters in your telescope to get as much as you can out of it. This one was seen by Messier, and it actually was one of those things he put together his list for. There was a comet that was known to be in that part of the sky when he was looking, and he actually thought this was the comet, which, as we know, that was why he put together his list. It was his list of things that aren't comets for people who were out looking for comets, because if you found a comet and you named it after the king, you got all sorts of honors and whatever. This is a barred spiral, and we're looking at it face on, which is why we can see it as a spiral. It's about 65 million light years away. Brightness is about 9.7. Again, you'll still have to use your telescope and maybe your binoculars if you've got really good eyes. Actual is about a minus 21.8. Luminosity of this one, it's minimal. It's only about 44 billion suns. So compared to the ones we talked about previously, it has less luminosity, so less mass to it. But again, lots of active star formation, so definitely worth taking a look at. 6 arc minutes by about 5.5, so close to 6 arc minutes square, which corresponds to an actual diameter of more than 100,000 light years. So much bigger than the whirlpool, more in line with the size of Milky Way and Andromeda. It's also the location of 6 supernovas that have been seen since about 1960. So 6 supernovas over about 70 years. It's a pretty good number. And remember, of course, those occurred sometime in the past. The light's just getting to us now. Our next object is Messier 5 in Serpens Kaput. This is a different type of object. It's a globular cluster. I like globular clusters too. Okay, so here we are right here. And here is sort of an image of what the globular cluster looks like. Obviously, it's going to be much more condensed in a earthbound telescope, but magnitude is about 5.6. So if you're in a nice dark area and you know where to look, some of you with very good eyes, I haven't had those in a long time, will be able to see it with your naked eye. Obviously, you're not going to be able to see much detail, but you're going to be able to point and say, hey, there's a fuzzy patch up there. Its diameter is about 23 light years, 23 arc minutes, 175 light years. So gravitational pull covers an area of about 400 light years. So it's, so it's anything up to 400, about 400 light years away would be bound to that area, but not the core itself. It's about 24,000 light years away. Messier, with his equipment, was not able to resolve any stars, but he could characterize the nebulous patch. There are a significant number of variable stars within M5. And the stars are whitish, yellowish type stars. They are much, much older, as with most globular clusters, in the on order of 13 billion light years. It's really beautiful. I say that about all globular clusters, that, for lack of better terms, I'll use my mother's diamonds on black velvet. Again, definitely a nice object to take a look at, and also a beautiful object to show to people at a star party. NGC 5248 is another galaxy. This time we're in Boötis. And okay, so I concentrated on spirals. I like spirals. They're pretty. And again, we can see lots of red and some blue bright regions in the spiral arms. So again, indications that whenever this light actually left, that's getting to us now, many billion years later. There was a lot of activity going on in this galaxy. Again, it's part of the Virgo cluster. It's about 50 million light years away. Parent diameter is about 6.5. Magnitude is 10.2. So this is not a naked eye object. But again, lots of star formation is visible in the arms as well as in the center region. And I just have one more object, and I'm at 7:48 on my clock, so I guess I can talk about it. This would be Epsilon Boötis, or Izar, which is one of the bright stars in the Boötis constellation. Izar, or also Pulcherima, simply means the most beautiful. It's a double star with an orange giant and a green-blue companion. Magnitudes are 2.5 and 4.9, and they're a couple of arc seconds away from each other, about 200 light years away. A significant difference in luminosities. One's about 400 times that of the sun, the other only about 27 times, which is still pretty impressive. Size, also pretty impressive. The companion star is about twice the size of the sun. The giant star obviously is much bigger, about 33 times the size of the sun. They're separated in reality by about 185 astronomical units, and their period around each other is more than 1,000 years. So that is my collection of objects in the sky for this quarter. So thank you very much, and we will talk again.
Well,
And now
we'll see if there's any questions, Mary.
I
if
thought the questions were afterwards. Okay.
Well, we do have you down for a breakout room afterwards, but our Facebook people are still on now, and they won't be here for breakout rooms. And
Oh, okay. That's fine.
so we'll wait a minute and see. If anybody on Facebook has a question for Mary, please go ahead and enter that so we can make sure and ask her.
You got a thank you from somebody named John on Facebook,
Okay.
Great.
but I don't see any questions.
Okay.
Oh, there's something that
Oh.
just came up.
Okay, what do arc minutes mean? This is from David.
Okay. An arc minute is effectively a three-dimensional is how we measure angular space in 3 dimensions. My rule of basically, if you think about a degree is 30 arc minutes. The minutes of arc are simply a different way in spherical geometry to represent an angular distance. So just think about 30 arc minutes is half a degree, and that's the size of the moon.
Okay, anything else from Facebook?
I do not see anything else.
Okay, we have one comment from Charles. Is anyone old enough to remember this? In 1968, an alien artifact in the shape of a rectangular solid was unearthed by NASA in the floor of the Clavius crater, 153 miles in diameter on our side of the moon. Then everything changed. I was working for NASA in Huntsville, Alabama at this time and followed this news closely. I don't see a question for Mary in that, so.
Yeah, but no, I do not remember that.
Okay. Okay, thank you so much, Mary. Yes, and we will see you later for the breakout rooms.
Okay, so I'm clicking the stop share button.
Okay. Terry, did you have something you wanted to say?
I've just put up the shared my slide for the Astronomy Festival.
Okay, good.
Which is April 9th at Brandy Fenton Park. 3 o'clock in the afternoon till 9 p.m. There's a list of all the activities going on. Starting at 3 o'clock, we'll have solar observing with telescopes with proper with proper filtering, interactive astronomy exhibits. We've got door prizes starting at 7 o'clock. And one of the prizes for a youth under 17 years old is a tabletop telescope. We have night viewing from 7:30 to 9, and anytime between 3 and 9, if you have your own personal telescope that you need help with, you can bring it down to the park and we can help you. Hopefully not at 9 because we have to start packing up at 9. So maybe like 8:30 would be the latest. Is there anything else to add to that? Okay. Hope to see the Facebook people there.
Yes, so Facebook, we're going to say goodbye to you in a minute here, but we really appreciate all of your coming to our meeting. We hope that you will remember us every first Friday of the month, and that you will definitely spend some time on our website, TucsonAstronomy.org. It has interesting information, and it has some activities for children. It has some information for teachers, and it has some astronomy videos. So, as well as a place where you can join the club or you can donate to the club. So we hope that you will play with our website and have fun with it and learn some things. And we look forward to seeing you again soon. Thank you so much for sharing with us. Okay.